very much, Matt, for introduction. And thank you very much all of you for coming. At the very beginning, I would like to say that it will be a difficult talk for me since today my grandmother died. So it's a pretty hard time, but I just dedicate this talk to her. So the talk is about my PhD, and basically it's about the very celebrated conjecture of Erdos-Hajnal that was stated some time ago, in fact in 80s, and it's still unsolved. It's one of the most interesting unsolved problems in graph theory. Definitely for me, but I think not only for me, since many mathematicians from all over the world tried very hard to prove it or disprove it, and so far nobody succeeded. So the main topic of this talk are my results, new results concerning the Erdos-Hajnal conjecture. So basically I will show the conjecture for new classes of tournaments for which it used to be an open question before. And at the very beginning, I would like to say that part of the talk is a joint work with Maria Szudnowski, my advisor at Columbia University, and Eli Berger from Haifa University. And the other part of the talk is a joint work with, again, Maria Szudnowski and Paul Seymour from Princeton University. So let's start. So basically, what's the conjecture about? So this is the short schedule of the talk. So I will describe the conjecture because I'd like everybody to understand at least the conjecture. Understanding the statement should be quite easy, and we don't have to go into details of the proofs, but it would be nice to see what are the main challenges and why it's still so hard to prove. And later on I will describe those new results. Basically this talk will divide into two parts. So the first part, in the first part I will prove the conjecture for new classes of tournaments called galaxies. And in fact recently I managed to extend those results for so-called super galaxies. I hope there will be time to talk about them too. In the second part of the talk, I will talk about so-called pseudo-celebrities. These are the tournaments with very interesting properties, and of course I will talk about them because they are very much related to Erdos-Hajnal conjecture. I will explain it later. So let's start with the talk. What's the conjecture? So basically the conjecture has its undirected and directed version. They are both equivalent. So let's state it with an original version, the one that Erdős proposed and Hajnal proposed some time ago. So in the undirected version, we have, let's fix a graph H. This is just an undirected, unweighted graph, just some arbitrary graph. And the conjecture basically says that if we take a bigger graph G, and we also know that this bigger graph G does not contain H as an induced subgraph. So you cannot find a copy of H anywhere in the bigger graph G. Then this bigger graph G has some very non-random properties, and those non-randomness of the graph G is measured in terms of the biggest clique or the biggest stable set. So basically the conjecture says that then the bigger graph G has a huge clique or huge stable set. And the stable set is a set of vertices such that there is no edge between any two of them. So it's another definition, another popular name is independent set. So, and the clique is a stable set in the complement. So basically the set of vertices such that there is an edge between any two of them. So why I say that this Erdős-Hajnal conjecture implies some non-randomness of G, because if we take a very random graph G, so we can think about n vertex graph in which every edge is chosen with probability 1 over 2, then it's easy to prove that. Oh, sorry. Okay. So basically, if we take a random graph, then this random graph with very high probability will have very small stable sets and very small cliques of logarithmic size. So the conjecture basically says that if we know something else about the graph, so basically if we know that the graph does not have H as an induced subgraph, then suddenly the really huge clique or really huge stable set appears in the graph. And the equivalent version for tournaments is as follows. So instead of undirected graphs, we have tournaments. And the clique and stable set are replaced by a single object, a transitive subtournament. What is it, a transitive subtournament? So basically, it's a tournament that does not have directed cycles. Or if we are computer scientists, we can think about it as a tournament such that you can order the vertices in a topological ordering. So there is a vertex. Yes? Sorry? So a tournament is a directed graph in which there is an edge, directed edge between any two vertices, but only one. So for any two vertices I and j, you have either directed edge from I to j or from j to I. So this is the definition of the tournament. So we can think about n players, and the edges, the directions of the edges indicate who won with who. So we have n choose 2 games on n players, and that's why the name tournament. So in the tournament version, the conjecture says that if we do not have any fixed H as a subtournament, then the bigger tournament contains a huge transitive subtournament. And again, that implies non-randomness of this bigger tournament, because if we take just a random tournament, it can be easily proven that the biggest transitive subtournament of this tournament is of logarithmic size. So suddenly, if we impose that there is no structure that is hidden there in this bigger tournament, then we go from logarithmic size to a polynomial size and to some epsilon. This epsilon, of course, depends on the smaller tournament H, but it's greater than 0. So this is what is the conjecture about. What we know so far, we don't know much about the conjecture, unfortunately. And in fact, probably this is the reason why I started working on that, because it seems to be a quite challenging problem in graph theory, since really good mathematicians were working on that without any success. So basically, we know the conjecture for some graphs, some tournaments and some undirected graphs, and very small tournaments and very small undirected graphs. And we also know the procedure that enables us to obtain the conjecture for bigger tournaments if we know the conjecture for smaller tournaments. This procedure, I will denote it as a substitution procedure. It was introduced by Alon, Solimoschi, and Pach, I think like 10 years ago. And maybe I will describe it a little bit, or maybe even it's a good time now to describe it. So I will go to the whiteboard. So basically, whenever I say that the conjecture that tournament H satisfies the conjecture, I mean that there exists some epsilon H greater than 0, such that if we exclude H from the bigger tournament, then the bigger tournament has a transitive subtournament of size and place, at least it's ordered in this epsilon. So what's the procedure that enables us to obtain tournaments satisfying the conjecture from smaller tournaments? So there are many ways to express it. Maybe I will just use the simplest one. So basically, if we have two tournaments, H1 and H2, and we know about both of them that they satisfy the conjecture. So basically, we can prove that there exists some epsilon H1 such that the conjecture is satisfied for this tournament, and epsilon H2 such that the conjecture is satisfied for this tournament. Then, if we create a bigger tournament, just making H1 out adjacent to H2. What I mean by this, every vertex of H1 points to every vertex of H2. Then we define a bigger tournament on H1 plus H2 vertices. And this bigger tournament can be also proven it also satisfies the conjecture. What epsilon is good for the bigger one? Definitely smaller epsilon than this one and smaller than this one. In fact, there is we don't know exactly exact value, but we know a lower bound on the epsilon for the bigger tournament. And it's of course a function of h1, epsilon h2, epsilon h1, and the number of vertices of h1 and the number of vertices of h2. So basically, this is the procedure that enables us to obtain other tournaments of graphs. For graphs, it's all exactly the same. For graphs, of course, we don't have directed edges. So if we have two graphs, h1 and h2, that satisfy the conjecture, then if we take just the union of them, it also satisfies the conjecture. Or if we take the graph obtained by gluing h1 and h2, what I mean by gluing, just make every vertex of h1 adjacent to every vertex of h2. Then it also satisfies the conjecture. So this is the analogous procedure for the undirected case. So in such a scenario, we can also prove the conjecture. And basically, this is the only procedure that enabled us to obtain infinite family of tournaments satisfying the conjecture. So it was the only, but then the galaxies appeared, so I will talk about what we managed to prove. So basically, we proved the conjecture for a new infinite family of tournaments that cannot be obtained using this procedure. And the other part of the talk will be also about the tournament, so-called C5 tournament. It was the only tournament of on five vertices for which the conjecture was a big open question. And for all other 5 vertex tournament, it was proven. And I managed to prove the C5 some time ago. So I will just talk a little bit, very roughly, about the idea of the proof. What's the C5? So far you know that it's some 5 vertex tournament, but I will define it now. So basically the C5 is the following tournament. So we have 5 vertices, and the outer cycle is a directed cycle, and the inner cycle, this one, is also direct. So this is C5. The only 5 vertex tournament for which the conjecture was open. It was quite frustrating because all other 5 vertex tournaments were galaxies. So they follow from our previous result of galaxies. But the C5 is not a galaxy. I will define galaxies later. But now just have in mind that it's not a tournament that belongs to this family. That's why it's quite hard. But I will prove it here. So it satisfies the conjecture.
Question.
Yes.
So in the equivalence between the tournament conjecture and the
Yeah.
actual Erdős-Hajnal, the epsilons, are they the same?
What do you mean? This, do you think?
In the previous slide.
Yeah.
Yeah. So the epsilon h is the same as the.
So for directed version, you deal with tournaments. So H is a tournament, and for undirected, you deal with undirected graphs. So
is the function the same function, epsilon?
No, it's no. In fact, it's nobody knows how to like. So even though it can be proven, and it's true that the two versions are equivalent, the mapping is very specific. So if you prove the conjecture for some tournament, then it's very hard to say what it implies for the undirected word. And if you prove something for undirected word, it's very hard to say what it implies for a directed word. However, it can be proven that if you know the conjecture for all tournaments, then you know the conjecture for all undirected graphs and vice versa. So, but the mapping is quite difficult. In fact, the mapping is like for a small tournament, you get a huge graph that is equivalent. So it's hard to say, like the epsilons could be really very different. And in fact, we even don't know whether we can state epsilon or the lower bound on epsilon as some nice function on like that could be expressible in terms of the size of the tournament. We don't know. Like I have a conjecture that epsilon of h is at least 1 over h when h is the order of the tournament, but we still don't know. So it's really like people have no idea even how this epsilon h looks like, could look like. Of course, we don't know whether the function in fact exists, but it's really hard to say anything about it. So So directed version is equivalent. That's why we'll deal with directed version, because in directed version, instead of cliques and stable sets, we have just one object that we have to deal with, transitive subtournament. So we know the conjecture for very small tournaments. We know the conjecture for tournaments obtained from the replacement procedure. And basically that's all. So in this talk, we'll learn how to prove the conjecture for new infinite family of tournaments. I will sketch the proof of C5. Even though it's a small tournament, but it was a big, like I spent about 4 months on that. And I remember I was in Italy on the conference some time ago. I was quite sure that C5 does not satisfy the conjecture. So I just announced that I would disprove the conjecture for C5. And then it turns out that I proved it for C5. So then at Princeton, I gave another talk proving it. But at least I proved it, so it was okay. Yeah. So, and in the third part of the proof, I would say something about pseudo-celebrities. I don't want to talk about them now because they require some extra definitions. I hope I will have time for pseudo-celebrities too. They are very much related to Erdos-Hajnal conjecture. So what is a galaxy? So a galaxy is a collection of stars. And we'll just use left stars and right stars. So what is a left star? So think about a set of vertices with one vertex, as one special vertex, which is colored green here. It's the center of the star. And the blue vertices are the leaves of the star. The star presented here is a left star because the center is on the left to the leaves. So what is a galaxy? It's just a collection of left stars and right stars. The right stars look in an analogous way to the left star. So we have one left star, one right star, and this union is a galaxy. So what I mean by this, you can be quite surprised because, okay, I defined some edges, some directed edges, but I do not define all directed edges. So if we take this tournament, the 6-vertex tournament, then we know some edges, but we don't know anything about the other edges. So basically, I draw only edges that go backward. So this is the convention that I will use later on because it's quite useful. So we will be we'll be dealing with tournaments for which there exists an ordering of vertices such that only few edges go backward. And that's why it's easy to draw them. So galaxies are examples of those tournaments. Not all tournaments with this property are galaxies because they can have some cycles too, but galaxies satisfy this property because basically, so in the galaxy case, the stars are disjoint, vertex disjoint. That means that, so every star is a tree, in fact, so that means that the set of backward edges is linear in terms of the size of the tournament. So whenever you look on this picture, just have in mind that all other edges that you don't know anything about in this picture, then they go forward. And the only edges that I drew are the edges that go backward. So now we have defined the tournament. So basically the red edges are exactly the backward edges. And this is a galaxy because this is a collection of one left star and one right star. And in the very general case, this is another galaxy. I think it can be reduced to a smaller tournament using this procedure, so it's probably not very interesting. There is also something that is called supergalaxy. So I will explain now what's the difference between galaxy and supergalaxy. So basically, the galaxy, from what I said so far, we knew that the galaxy is a collection of vertex disjoint left and right stars. But there is also one extra condition that each galaxy has to satisfy. And the condition is as follows. If we fix any single star, and we consider the set of its leaves, then there is no center of another star which lies between leaves of a given star. So basically, if you just consider centers of stars, we won't find the center of the star inside the leaf structure of another star. So that means that, for example, this tournament, at least if we express it using this ordering, it's not a galaxy, because now we have a center of this left star that is between the leaves of another left star. However, in the supergalaxy case, this condition is relaxed. So in fact, we allow the centers of stars to lie between leaves of other stars. However, if this is the case, all the leaves of the stars have to be outside the leaf structure. So basically, this is a super galaxy according to this definition, but it's not the galaxy. So the proof of supergalaxy is quite complicated, even though it's an extension of a galaxy word. So I won't go into details of the supergalaxy proof, but I would like to explain very roughly how to prove the galaxy case. So some definitions. So I think we don't need to read it. The left star and the right star were defined by me before. And as I said before, we'll be also dealing with ordering of vertices. Because if we want some edges to be backward edges, the term backward edges has a sense only if we fix some ordering. Because an edge that is a backward under some ordering could be forward under other ordering. So we can think all the time about, so we take some tournament, we fix some ordering of vertices. If we take galaxies, we will fix this galaxy ordering. And under this ordering of vertices, we will do something with the tournament, and we will proceed, etc. So, and backward edge basically under ordering is defined like that, but I explained it before. So, left star, the same definition, and the star, as I said before, collection of left and right stars. And the galaxy tournament, I also explained it before. So just so the tournament such that there exists an ordering of vertices under which such that under this ordering the set of backward edges is a collection of disjoint left and right stars, and there is no center of a star between leaves of another star. And as I said earlier, this last condition can be relaxed if we take super galaxies. But I won't talk about super galaxies during this talk. So the theorem is that the Erdos-Hajnal conjecture is satisfied by every galaxy. So if we take a galaxy, then always exists epsilon h greater than 0, such that if this galaxy is excluded from a bigger tournament, then the bigger tournament has a huge transitive subtournament. And somebody, in fact, asked me, okay, so what is this epsilon h in terms of a galaxy? Since I proved this epsilon h, then and we have a huge subtournament, then what is it? Like, can we say it's like 1/2 always, or maybe it depends somehow on the size of the tournament? So it depends, but it's like double tower function. Of the order. So it's, for mathematicians, it's huge because it's still this epsilon, it's constant, but I cannot express it in any sense, interesting way. It's really small. It's like 1/2 to 2 to 2 to 2, etc. But it's greater than 0. So it is all that matters for mathematicians. We don't care about anything else. But in fact, there is some good news. So the reason why this epsilon h from the proof that I found is so small is that I use regularity lemma, which is a powerful tool in graph theory. However, the drawback is that all the constants that are used in this lemma are extremely small or extremely huge, and that is also the reason why this epsilon is so small. But it's possible to get rid of the regularity lemma, and if we do it, then the epsilon will be a little bit better. So if you ask me now what will be the epsilon, I still don't want to say, because it will be definitely smaller than the double tower function, but still quite huge. But a nice function of the order of the graph, so like 1/h to h to h. So it's better. Okay, so let's go to the rough idea of the proof. One more thing. The other interesting tournament that we were dealing with for a while was the directed path, PK. So what's a directed path? It's a tournament on k vertices such that there exists an ordering, such that under this ordering, the backward edges just form a path. So you can think, so we have edges 2, 1, 3, 2, 4, 3, 5, 4, 6, 5, 7, 6, 8, 7, and all other edges are forward edges. So this is the path. And the undirected path is a huge open problem. We still don't know whether the conjecture is true for undirected path of length at least 5. However, the directed path is a consequence of our galaxy theorem, because it turns out that even though this ordering is definitely not a galaxy ordering, because this is not the collection of left and right stars, but we can a little bit shuffle the vertices. And if we just switch 2 with 1, 4 with 3, 5 with 6, and 7 with 8, then we get the following scenario. So basically now the backward edges, these are the red edges, they definitely form a collection of left and right stars. And you can do it with every path, not only this one of 8 vertices, but an arbitrary path of k vertices. And the same procedure works, so just switch first and second, third and fourth, etc. So in fact, this is a galaxy, even though the path ordering, it's not a galaxy ordering, so at first glance, it doesn't look like a galaxy. So this is just a trivial consequence of a galaxy theorem. So this is just a nice corollary. So yeah, and this is basically what I said before. And maybe before going to the proof, the very last thing that I want to do in the first part of the talk is the tournament C5. So, as I said before, it's not an outcome of the Alon's substitution procedure, so we cannot use their results to prove the C5. Finally, it's not a galaxy tournament. That means that it's not a corollary. Like a path, it's a corollary of a galaxy theorem, but C5 is not. And as I said before, it was known for all other 5-vertex tournament, the conjecture. So this one was of big interest. I explained before how it looks like. So we have 5 vertices. The outer cycle is the directed cycle, and the inner cycle is a directed cycle. But in fact, because we are dealing here with ordering of vertices of the tournament, we will consider a slightly different representation of C5. So basically, we take 2 orderings of C5 that are presented on the slide. One, the top ordering is, I will denote it the tree ordering. Why I denoted the tree ordering? Because the set of backward edges under this ordering forms a tree. And the second ordering, it's not a tree ordering because we have a cycle, a triangle of backward edges, but it's also very important for us. Both those tournaments that we see on the right side are in fact the same as the one on the left side. So they are both C5s. But because we have those 2 representations of C5, it was possible for me to prove the conjecture for C5. So in fact, those 2 orderings of vertices are extremely important. Like this is the key to prove the C5 conjecture. So this is the theorem about C5. So we know that it satisfies the conjecture, but as I said, epsilon is extremely small. And now let's go to the sketch of the proof. If there are any questions, I would like to answer some of them now, because it's just, I would probably start some more technical things. So if there are some more general questions about the conjecture, then maybe that's a good time to ask them now. If not, I will just as I said, I want to very roughly describe the proof. It's like for me it's super interesting, but I think it's also quite technical, so I don't want to go into details. So as I said before, it uses regularity lemma. I will explain what it means later, and like these are the key things that are used in the proof. So basically regularity lemma, it's a powerful tool, and then we will somehow extract from our H3 graph a big linear set that will be exactly out adjacent or exactly in adjacent from a big transitive set. That enables us to obtain a bigger transitive tournament satisfying the conjecture, and in fact that enables us to prove that the tournament will be of size at least polynomial size. So the regularity lemma, I think nobody likes definitions, so maybe I will just draw something on the whiteboard. So you can skip those slides. So So basically, the regularity lemma says that if we take big enough, it works for both directed and undirected graphs. So I will explain it in terms of tournaments, since we are doing for tournaments now, but it's also for undirected graphs. So as soon as we have a huge tournament, so the regularity lemma basically says that every big enough tournament can be partitioned into, like its set of vertices can be partitioned into a constant number of sets. So we have some constant that doesn't depend at all on the size of the bigger tournament. In fact, this constant is very huge. Like all the constants in regularity lemma are extremely huge or extremely small. So this one turns out to be extremely huge. So, but it's constant. So we can partition in the constant number of sets, each of size approximately. So if we have k sets, this is some constant, we will give size approximately n over k, such that if we take any two sets of vertices from this partitioning, so denoted by ai and aj. So we take two sets from the partitioning, ai and aj, and then we can measure some edges go from ai to nj, some edges go from aj to ai. So the directed density between ai and aj is basically the total number of edges going from ai to aj divided by the product of the size of ai and the size of aj. So we can think about this density is 1 if all the edges go from ai to aj. Because then the number of edges going from ai to aj is exactly the product of ai, the size of the ai times the size of aj, and we divide it by, so we normalize it by the product of the size of the set, so we get 1. So density 1 means all edges between ai and aj go in fact from ai to aj. There is no edge going from aj to ai. Density, the directed density 0 from ai to aj means that all edges go from aj to ai. So basically what regularity lemma says, it says the following thing. So calculate the directed density from ai to aj. This is some number between 0 and 1. So I will denote it by d ai aj. It's a number from 0, 1. And then take some subset of ai. It could be much smaller than ai, like of size epsilon times the size of ai. It could be arbitrary subset. It can't be too small, but it can be relatively small. So epsilon is some constant that we fix at the very beginning. So we fix epsilon, and then we get k as a function of epsilon. But k is only a function of epsilon. It's not a function of the size of the tournament itself. So we take a smaller subset of vertices in ai, and we take a smaller subset of vertices in aj. And then we want to calculate the direct density between those two smaller subsets. So I will denote this one by ai prime, and this one by aj prime. So now we calculate the direct density from ai prime to aj prime. The regularity lemma basically says that then those two direct densities are very close to each other. So basically the difference between them is at most epsilon. So I don't know if I will just erase it right now. So d.ai aj minus d.ai prime aj prime is at most epsilon. And how can we think about this lemma? So basically, let's think about the following experiment. So take ai and aj and define the edges just by choosing edges at random. You flip a coin. It doesn't have to be with probability 1/2 each direction, but you flip a coin and you get some distribution. And if you do it in the random way, then it's easy to prove that with very high probability, if we take the smaller subset here and the smaller subset here, and you calculate the directed density, then it's pretty close to the directed density between the bigger sets. So you can think about the regularity lemma. It says that you can partition the vertices into a really small number of subsets, such that the distribution of edges between any two sets are like in a random model. So where independently at random we choose an edge to be from AI to HA with probability some P, and from HA to AI with probability 1 minus P. So this behavior between those two sets of vertices is like a random behavior. It doesn't have to be with probability 1 over 2 in each direction. It could be divided like some like 3 over 4, and that doesn't matter. But it's a probabilistic distribution that very well approximates what's going on for that graph. So a random graph somehow between those sets approximates every graph that is big enough, which is a very pretty amazing thing. And it's quite amazing that the K really does not depend on the size of the larger graph. So we fix some regularity parameter, epsilon. This is like a precision parameter. And then K is just a function of epsilon. It really doesn't depend on, so you fix epsilon to like 1 over 100. And then you get K, which is a tower function. It will be like but you know that every graph may have a huge number of vertices, will be partitioned into just K sets such that the edges going between those sets behave like a random distribution. So this is basically the regularity lemma that we will use, and these are the definitions that I think it's better to explain it in that way. So basically, what the regularity lemma says, I just said it, that every graph can be partitioned in such a way. So it doesn't matter whether the graph is directed or undirected. There is also something that is called the universal lemma. It's quite important. I would like to, and again, don't read this horrible statement. I will just explain it in a nice way here. So regularity lemma, it's a link between Erdős-Hajnal conjecture and universal graph lemma. It's a link between regularity lemma and Erdős-Hajnal conjecture. So if we understand the universal graph lemma, we will understand why regularity lemma is so important and so convenient to use when we dealing with Erdős-Hajnal conjecture. So basically, the regularity lemma says something as follows. So assume that you have a big graph, and it can be partitioned into some subsets, some constant number of subsets, like 100 subsets. So we take 100 subsets, and we know that every pair, if we take any two sets from this partitioning, and if we calculate the directed density between this set and this set, it won't differ much from the directed density between some smaller set from this set and some smaller subset from this set. Basically, I would denote this condition by the regularity condition, because in the regularity lemma we assume that we can find a partitioning such that every pair is epsilon regular. So epsilon regular means that if you take subsets that are at least epsilon times the big set, then the directed density does not differ much. So assume that every pair of sets here is epsilon regular. And assume furthermore that this directed density between any two sets from this partitioning is some constant, or it's bounded from below from 0 by some constant. So the directed density is equal to just here. It's at least some lambda, which is lambda is greater than 0. And it's at most 1 minus lambda, where 1 minus lambda should be less than 1. Why I think I explained it in such a way? Because in fact we're dealing with an infinite number of graphs. So for every graph we get some partitioning and we can get some D. And we don't want those D to go down to 0 or to 1 as n goes to infinity. We want to say that they are bounded below by something greater than 0. and bounded from out by something less than 1. Also, and we can think about all the densities in such a way. So, for example, here is like 3 over 4, and here is like 5 over 6, and here is like 99 over 100. So then the universal graph lemma says that if we take if you can fix now some graph of 100 vertices or tournaments. So just imagine some tournament of 100 vertices. It doesn't matter which tournament you take. Then this tournament will be found somewhere in this huge structure, and then you use subtournament. In what way? So every vertex will be found in a single vertex in a single cell. So we need 100 parts of the partitioning because we need to find the single vertex in the single cell. So we take, for example, you can take this C5 tournament, and now let's take those 1, 2, 3, 4, 5 sets. And you will find one vertex here, one here, one here, one here, one here. So it's possible to find the vertices in such a way that if we now take this tournament induced by those 5 vertices will be C5. And you can do it for every tournament. So, so basically you pick some tournament, and for n large enough, if you know that there exists this partitioning, then you can find any fixed tournament as a subtournament. So basically, if you would like to prove the Erdős-Hajnal conjecture, we are only interested in tournaments for which such a partitioning does not exist. Because if the partitioning exists, then it implies that we will get a copy of anything that we want. So we are only interested in tournaments that does not have such a partitioning. And this is quite important. In fact, this is the first trick that we will use in the proof of the galaxy case. So maybe, yeah. So this is before. I don't want to go to the to the details of the proof. I think I would like to say something about so-called pseudo-celebrities now, because it doesn't require all technical details, and is a quite important part of the research too. So from the galaxy parts of the talk, you can roughly have an idea that we use regularity lemma. You don't know exactly how we use it, but I think it's too complicated to explain it now. So let's talk about pseudo-celebrities. This is an interesting part of the talk too. So what are pseudo-celebrities? So I think I have still 10 minutes. So it's perfect time just to, I promise there will be no proofs now at all, but I just want to state some results and make you interested in that, because it's amazing stuff, amazing theorem. So pseudo-celebrities, as I explained before, are pretty much related to the Erdős-Hajnal conjecture. So the Erdős-Hajnal conjecture basically states that we always get this epsilon h, such that if a big tournament doesn't contain h, then it contains the transitive subtournament of size n to epsilon h. But we can think about even a stronger property. Can we say something about tournaments? So assume that we want not only a polynomial size transitive subtournament and some epsilon, but a linear size. So we want to find tournaments having the following property. If we exclude the tournament from a bigger tournament, if we exclude h from the bigger tournament, then the bigger tournament contains a transitive subtournament of size epsilon times n, not n to epsilon. So something even stronger. A huge transitive, a huge fraction of this to a bigger tournament is just a transitive tournament, the simplest possible tournament that we can think about. So now the question is, the first question is whether all the, maybe it's also the case that we can strengthen the Erdős-Hajnal conjecture, and maybe we can conjecture that all tournaments satisfy the conjecture in the strongest linear sense. It's not true. So it's easy to prove that some tournaments simply does not satisfy conjecture in the following strong sense. However, it's possible to describe all the tournaments that satisfy the conjecture in the linear sense. So there is a structural theorem that enables us to build bigger tournaments satisfying the conjecture from smaller ones, and we know that this is the only way to obtain tournaments having this property. So we have a structural theorem, and this is the work by like 7 people. So like Professor Seymour, my advisor, Marek Choromanski, Alex Scott, Danny Berger, Stefan Thomas, Martin Lev, and me. So it was a really nice work we were working on. But it's not, so those tournaments that satisfy the conjecture in the linear sense will be called celebrities. In fact, previously they were called killers, but Professor Seymour decided to change the names because it was cruel. So changing them from killers to celebrities. And now we are talking about celebrities, not killers. So what is a pseudo-celebrity? So pseudo-celebrity satisfies the conjecture in almost linear sense. What I mean by this, so H is a tournament H is a pseudo-celebrity if the following holds. If we exclude H from the bigger tournament, then this bigger tournament, it doesn't have to contain the linear size transitive subtournament, but almost linear size. So by this I mean n over log n to some power. So it's definitely much better than polynomial size n to epsilon. It's almost linear. And this is a nice story because, in fact, when we proved the celebrity theorem, we thought that this is everything that we wanted to say about this case. And then I remember the talk, I had a talk with Professor Joel Spencer at NYU University. I showed him some of my results concerning the conjecture, and talked about that we had a problem with one 6-vertex tournament for which we can prove that it's not a celebrity, but we cannot prove that that there is no slightly sublinear function that is good for it. For all other tournaments that we took into consideration, it was easy to prove that there is a polynomial times upper bound on the Erdős-Hajnal conjecture. For this one, for the 6-vertex tournament, so-called delta 2 to 2, it wasn't clear at all. And he suggested, in fact, that maybe the case is that this tournament satisfies the conjecture in the linear sense. So this is delta 2 to 2. So a 6-vertex tournament such that 1 and 2 are both out adjacent to 3 and 4 and in adjacent from 5 and 6. And 3 and 4 are both out adjacent to 5 and 6. So we could prove that this is not a celebrity using a very heavy probabilistic machinery, but we couldn't find any polynomial bound, upper bound on the Erdős-Hajnal coefficient. So he suggested that maybe the case is that there is no one. Maybe it satisfies the conjecture in almost linear sense. And so he suggested that there are so-called pseudo-celebrities, and this is just a basic pseudo-celebrity, the smallest possible pseudo-celebrity. And I started working on that, and then my advisor started working on that, and her former advisor, Professor Seymour, started working on that, so we're all working on that. And after several months, we managed to prove the structural theorem of all the pseudo-celebrities, so they do exist. And this is, in fact, the smallest pseudo-celebrity. The old pseudo-celebrities look as, I will show you how, yeah. So these are all the pseudo-celebrities. So this is just a scheme. It doesn't tell you much, but basically it tells you that if you have two pseudo-celebrities, and if you make one out adjacent to the other one, you get a pseudo-celebrity. But there are so-called basic pseudo-celebrities, the most important pseudo-celebrities that were the most difficult to prove, and delta 2 to 2 is one of them. So basic pseudo-celebrity is obtained by taking a transitive tournament, make it out adjacent to another transitive tournament. So basically this piece is a bigger transitive tournament, and taking two extra vertices. Make those two extra vertices out adjacent to the first part of this bigger transitive tournament, and out adjacent from the second part of this transitive tournament. And this turns out to be a pseudo-celebrity. So delta 2 is just a very special case in which k and l is just 2. So they all specify the conjecture in almost linear sense, n over log n to some power. The power depends on the size of the pseudo-celebrity. The bigger pseudo-celebrity, the bigger the higher power. So the weakest, the exponent is. However, that was the reason why we couldn't prove anything better than we could just prove that these are not celebrities, but we couldn't find any polynomial bound upper bound because it simply didn't exist. And what is quite surprising about this, if we go to undirected word and ask the similar question, are there any undirected graphs which satisfy the conjecture in almost linear sense, then the questions are trivial. So the answers are trivial. The answers are that there are only finitely many graphs that satisfy the conjecture in almost linear sense. So basically, some very small graphs, just 4 vertices, very trivial graphs that you can explicitly describe easily. So it's nothing to be difficult to be proven. However, in indirect scenario, somehow the whole question is much, much more complicated. And in fact, I am pretty satisfied that it turned out that pseudo-celebrities exist, since it's really great that this word somehow behaves in a completely different way than the undirected word. And it's like Professor Spencer always had great intuition, but he was right once more. So because of him, I in fact started working on that. So that was a good guess to assume that there is some mysterious family of tournaments that satisfy the conjecture in a very, very weak sense. It turns out that it exists. So mathematics can be very surprising, and that's what I like about it. So I think I would like to finish now. I don't want to go to very precise details of all those proofs. It's impossible to say it just in 1 hour. Yeah, at the very end, I just wanted to say that the Erdos-Hajnal conjecture is a fascinating topic for me. I still didn't prove it. Otherwise, I would probably present some results here, even if there will be some partial results. But in fact, I think that the conjecture is not true in the general sense. So I want to disprove it now. And the reason is that the conjecture so far was proven only for some very specific infinite families of tournaments. Even if we take galaxies, these are very non-random tournaments. They have ordering under which the set of backward edges is very small. It's of just of linear size. So you can think about taking a really random tournament and asking the question whether EH is satisfied by this random tournament. We have no idea how to deal with tournaments like that. It's a big open question. My guess is that we don't know how to do it because simply it's not true. So hopefully by the end of PhD I will be able to give some probabilistic counterexample and finish the working on the conjecture. Thank you very much once more for that. It was a pleasure for me to give a talk here in this wonderful place. And yeah, if you have any questions, just let me know. Thank you once more. Find some probabilistic model. So you want to find a graph that does not have big transitive subtournaments and does not have some copies of some fixed graph H. And this graph probably needs to be chosen as taken from some probabilistic distribution. So I think it would be hard to explicitly say how those but just use some probabilistic model and prove that with zero probability such a graph exists. So of course, the question is, I think it's complex somehow, if I decide to what probabilistic distribution I would like to work with, I can use the computer to try to verify my guess to this proof. But the problem is that if I would just, to disprove the conjecture, I really need to find an infinite family of tournaments. Because if you can't find just a single tournament. If you find a single tournament and it does not contain H, and it does not contain the transitive tournament of size n to like 1 over 100. Maybe it contains n 1 over 1,000. Or not 1 over 1,000, maybe 1 over 1 million. So you know, like you have to find the infinite number of tournaments such that this epsilon goes to 0 so far. So that's the problem. So, and now I have no idea what probability distribution described. I used some probabilistic methods to prove in the model to prove that the conjecture is satisfied in a very weak sense. What I mean by this, almost every graph H inside the conjecture satisfies it with epsilon H at most 1 over H, when H is the number of vertices. So it's a pretty small coefficient, but still I couldn't go beyond 1 over H and get something much smaller. So the question is, what are the distribution I should take? And in fact, if I want to find precise mathematical proof, just compare this, giving some guess how, but you know, it's hard to like start simulating something if I don't know what the model I have to work with. Because I have no idea now what distribution is the right distribution. For the question.
Did you define what a hero was?
So hero is basically a celebrity. It's the same.
It's a celebrity.
Yeah. So celebrity is a tournament that satisfies the conjecture in the strongest linear sense. So if you exclude a celebrity, then suddenly you have a linear-sized transitive subtournament in the bigger tournament. The reason why we used two names, hero and celebrity, was that in fact we had two different definitions of a celebrity that turned out to be the same. But it wasn't clear at the first glance that they were the same. So the first definition was exactly this one that I said about the linear-sized transitive subtournament, and there was another one that had something to do with chromatic number. And it wasn't clear at all at first glance that they were equivalent. We thought that we were working on two different classes of tournaments. And then it turned out that these definitions are the same. If tournament satisfies this, it also satisfies this one. But the equivalence is quite difficult. It's like the whole article is in fact about this equivalence, so that's why we used two different names. So hero was related to chromatic number first, celebrity to this linear-sized transitive subtournament, but then it turns out that celebrities are just heroes and heroes are celebrities.
Thank you.
Thank you.